could be related to that, actually. Yeah, this could be another. This could be another explanation. This could be another explanation. More or less, is that frequency? Is that? Is around? See, is around 1 second, I think. 0.1 or 0.1. Yeah, this could be another explanation, for example. And after the average power density spectrum analysis, we perform for the first time in this case the individual power density spectrum analysis. There were some statistical issues before because it is difficult to fit the individual power density spectrum of each gamma ray burst, but it's important because we can extract information about each individual case, so we can look for possible coherent for possible periodicity in the light curve, and we can derive information about the variability of the individual cases. The statistical problem was that for the individual power density spectrum, the signal fluctuates very wildly. So you have there is statistical problem in the sense that you have to assume a specific likelihood in order to fit this. And we adopt, I don't want to go in detail, but we adopt some Bayesian approach, which involve a set of Markov chain Monte Carlo in order to fit the individual power density spectrum. We use two different functions to fit the individual power density spectrum, a band power law or a simple power law. The physical meaning of these two different functions is this one. I mean, in case we observe a break in the power density spectrum, this means that there is a typical duration of the pulses in the light curve. We call dominant time scale, a characteristic time scale of the duration of the pulses in the light curve. In case we fit with a simple power law, we don't find any evidence of a specific dominant time scale. So this means that all the pulses have different duration in this light curve. One of the main results of this analysis is this one. We find a connection between the spectral properties of gamma ray bursts and the timing properties. We find this highly significant anti-correlation between the peak energy of the nu F nu spectrum. This is a typical spectrum of a gamma ray burst, which usually is fitted with an empirical law called band power law. It's a broken power law. And you can find for each gamma ray burst the value of the peak energy. The peak energy is connected in some way to the slope of the red noise of the power density spectrum. Essentially, this result is telling us that for higher is the value of the peak energy, shorter will be the time scale variability in the light curve. You will have variability up to very short time scale. At first, yeah.
Which is what you showed at the beginning.
No, because in that case, we were observing different energy range, and we observed that at different energy range, the spectrum is getting flatter. In this case, it's not different energy range. We are talking about the peak, a parameter, a spectral parameter. The peak energy is higher, the spectra is flatter. It's not connected with what we were saying. What?
It is consistent with
Yeah, no, it's consistent with the previous one, but it's not the same thing.
You have more power at high frequencies when you have a greater energy range.
Yeah, it's consistent, but we are showing something different now.
Way of looking at it, but it's in the same direction.
It's going in the same direction, yeah. And okay, at first we test the reliability of this. So we saw that for higher value of signal to noise, the significance or the correlation grow. So this is an indication. Another indication is that passing from the observer frame to the rest frame, the significance of the correlation grow. So this means that we are observing something. This is telling something about the physics, the intrinsic physics of the source. There is one of the theoretical models proposed to explain the prompt emission predict something like that. like in the magnetically dominated emission model, we have the peak energy is related to the gamma prime, and the pulses, the duration of the pulses is related to gamma prime. Gamma prime is the relativistic factor of the material accelerated along the magnetic field in the magnetic reconnection region. So, according to this, we should observe something like that. In the framework, in the classical internal shock model, the internal shock model is the classical model proposed to explain the prompt emission of gamma reverse. You have different shells impacting each other and emitting a signal, so the prompt emission. And but in the framework of this model, this result is not straightforward. You have to put strong constraint on the model in order to obtain something like that, actually. I'm not going in the detail, but I can explain later if someone wants.
Looking at your plot down there,
yeah,
there is a certain correlation. The spread about it is huge.
The spread is huge, but you cannot use, for example, this correlation to standardize gamma ray bursts, for sure. But the fact is, you can constrain the physical model. That's the point. So we are using that to extract information, physical information. So the other model we take in consideration is the photospheric model. It's not clear in this model if you can reproduce this kind of correlation. Actually, here in this model, you have that the peak energy is mainly connected to the viewing angle, the angle between the jet and the line of sight. And if you go more offside, you have lower value of a peak. I don't understand exactly. We try to figure out, but I don't know exactly how the variability can change going to outside, more off-axis from the jet. But we are trying. I think that in putting some constraint here, making some assumption, you can reproduce the same result, even in the photospheric model. Another important result is that for the cases in which we found a typical duration of the pulses, for all the cases in which we found a break in the power density spectrum, so a typical duration of a characteristic time scale for the pulses, this characteristic time scale is related in some way to the total duration of the event. There is no trivial explanation for this. We found this result. The theoretical model doesn't talk about that, doesn't predict. No one of the theoretical model predict this kind of stuff, and we don't find any reason why should be something like here, for example. Why doesn't it? Actually, we simulate this kind of light of GRB in order to see if there is some selection effect in our analysis, and if they exist, we should observe that. So there is a real correlation, and it's observed even in this is the Fermi data, but it's observed with the Swift data, with BeppoSAX data, so it's something that we found. It's a result that is not explained yet.
A16 means that the total duration of the event...
It's the normalization of this fit.
That refers to the...
Is 60 times.
So the prompt lasts for 60 times longer than the typical variability scale?
Okay. In the... The point is that the normalization change when we take the slope is the same, but the we don't know why, but the normalization change when we take in consideration Swift data or BeppoSAX data.
Does it change a lot?
It's 45, I remember. Yeah, change.
50 plus minus 10%.
Let's see.
50 times the typical
Mm.
variability scale. That's
Mm-hmm.
the total duration of the prompt.
Mm-hmm. Then, for the first time, we we studied the power density spectrum of short gamma ray bursts. So for the first time, actually, we analyzed the timing properties of short gamma ray bursts. No one did before. We look for possible periodic, quasi-periodic feature in the light curve of short gamma ray bursts. Why? Because some theoretical model propose a kind of periodicity, a quasi-periodic signal coming from the disk around the innermost stable circular orbit. So there are some theoretical models that predict some kind of periodicity. So we look for this kind of periodicity. We didn't find any evidence of periodicity up to very high frequency, up to 5 kilohertz. We found two features about 2 sigma, but this is perfectly consistent with statistical filtration. So no evidence of coherent pulsation. An interesting result from this analysis is that the slope of the power density spectrum of short gamma ray bursts seems quite similar with the slope of the power density spectrum of the long gamma ray bursts. And this is something interesting. Here we can observe the slope of long gamma ray bursts, the distribution of the slope of long gamma ray bursts and the distribution of the short. We can see that the two distributions are quite similar. So maybe there is a common mechanism at the origin of the variability, a common physical mechanism at the origin of the variability in short and long gamma ray bursts. This is suggesting something like that. Then, for looking at the electromagnetic signal, we try to find some hint of the possible progenitor. We test the model proposed for a black hole neutron star merger. There was a paper by Stone et al. 2013, which proposed a sort of periodicity for short gamma from a merger between a black hole and neutron star. Essentially, we have a misalignment. In general, for a merger between a black hole and neutron star, you have a misalignment between the equatorial plane of the central black hole and the disk. And you have a sort of precession motion and a sort of lighthouse effect due to the fact that the jet is directed along the axis of the disk. So you have a lighthouse effect. So a sort of periodicity like in the pulsar, for the pulsar, but in this case, the periodicity is evolving very fastly according to this law. So we try to look for this kind of periodicity. See, something like that. You should observe something like that. A sort of a periodicity that evolves with time. So we focus our analysis of the signal of the short gamma ray burst, the T5 sigma. The T5 sigma is the part of the signal that stands above the background level, about 5 sigma above the background level. So we focus on the signal of short gamma ray burst, and we the only way we found to analyze, to study this evolving periodicity is redefine a new scheme, a new binding scheme in the light curve in order to reconduct the evolving periodicity to a constant periodicity. And then you can analyze that light curve with the normal power density spectrum looking for the coherent signal. I mean, it's the only way you can use it. There is no timing technique to study the evolving periodicity. So in order to do that, you stretch the light curve and you reconduct the evolving periodicity to a constant periodicity. We simulate this kind of light curve, and we found that our technique is actually powerful. We should observe this kind of periodicity if it exists. We didn't observe. But the point is that we are sensitive just for a subsample of 14 short gamma ray bursts, because the signal to noise should be higher than 35, let's say, in order to be able to detect this kind of periodicity. So this is upper limit versus signal to noise. So of course, we are higher is the signal to noise, more sensitive we are. But this is normal. We are sensitive just for a subsample of 14 GRB. So let's draw some conclusion from the timing analysis. From the average power density spectrum, we see that we have short time scale variability, the short time scale variability is dominant in the higher energy channel. We have a break in the power density spectrum, so a characteristic pulsation around 1 second for long gamma ray bursts. Then we had a connection between the spectral and timing properties, which is very important in order to constrain the physical mechanism. And we saw that there is a connection between the characteristic time scale of the pulses and the overall duration. For the short gamma ray bursts, we don't find any evidence of periodic or quasi-periodic oscillation up to kilohertz. So, and we found that this power density spectrum is similar for long and short, so maybe there is a common mechanism of the origin of the variability, a common mechanism ruling the variability in the two different events. We don't find any evidence of evolving periodicity, so maybe, okay, the sample is very small, so we cannot draw firm conclusion here, but we can say that maybe the black hole neutron star merger is not dominant in the fraction of population of the progenitor of short gamma ray bursts. Then I shifted my interest from the prompt emission to the afterglow. So I started to study the X-ray, optical ray, and radio afterglow light curve. And basically, I was involved in the optical follow-up activity with the so I joined the Liverpool group, the Liverpool telescope group. The Liverpool telescope is a very important telescope for the optical follow-up of gamma ray bursts because it is a robotic telescope which take from the satellite the position of the GRB, repoint automatically, and take the images basically immediately after a few seconds from the detection. And it's very important because it gets a polarimeter at the focus. So we measure the polarization of gamma ray bursts, and we measure the polarization of the reverse shock component. When we have in the physics of the shock, we have a forward shock and reverse shock by the interaction of the blast wave with the interstellar medium, and analyzing the polarization of the reverse shock means analyze the polarization of the ejecta. So we are extracting information about the polarization of the GRB. So they measure this 20% polarization in this case in the paper of 2013. So there is it seems that there is a large-scale magnetic field involved in this kind of phenomenon. Liverpool telescope? Two. Ringo is the instrument, is the polarimeter. No. Is at the focus of the Liverpool telescope. Is at the optical polarization. We are talking about optical. La Palma. And they are working on the study of the gamma ray polarization, but there are some issues for the instrumentation. It's very difficult to measure the polarization at that energy. And I use also a network of telescope, a global network of telescope, in order to perform the follow-up activity of gamma ray bursts. This is important because gamma ray bursts can be at every hour of the day, so it's important to have a global coverage. I can repoint to the gamma ray bursts at any time, more or less. So Las Cumbres Observatory Global Network is a set of 1 meter and 2 meter telescopes. The 2 meter telescopes are in Hawaii and in Australia. The other in Texas, Chile, South Africa. They are building something in India. So I wrote a set of scripts to optimize the optical follow-up analysis, so to submit the request, download the image, fit the astrometry, identify the optical transient, and I perform photometry of these images in order to extract information about to derive the light curve of gamma ray bursts. And in some cases, I also discovered the host galaxy of the gamma ray bursts. Okay, the study of the optical afterglow is very important because studying the afterglow light curve, we can extract information about the microphysics parameter. We can test the synchrotron shock model proposed for this kind of emission. we test of course the model, so the reverse shock and forward shock component. So we are checking if exists a reverse shock and forward shock component. And mostly importantly, we extract information about the jet geometry, because at some point in the light curve of the afterglow, you have a break, an achromatic break, due to the jet that is giving information about the jet geometry. So the angular spread of the jet. And another, the very challenging part of in this kind of research is the detection of the very high energy counterpart of gamma ray bursts. Because the very high energy counterpart now is something very mysterious. I mean, we don't know if the very high energy emission is related to the afterglow or to the prompt emission, if so to the physics of the afterglow, to the physics of the prompt, or maybe to another physical process involved in the gamma ray burst physics. Because we know, what we know is it exists, because we detect it with Fermilab, so it exists a gamma ray emission. And it begins, in some cases, it seems that it starts before the prompt, for some cases. I saw that in some cases they discovered that maybe this kind of emission starts before the prompt and can last much more longer time of the prompt. So it's very interesting, would be very interesting to detect this emission with OAK, for example. And I'm involved in a project in order for the follow-up of gamma ray bursts with OAK. And to study even give an upper limit for this kind of emission would be very important in order to constrain the physical model, to derive information about the Lorentz factor, or to derive, to test the Lorentz invariant, the Lorentz invariance with this emission, checking the different time, arrival time from these photons with respect to the other. So it would be very important to study this kind of emission. And this is just a short list of my publication.
Thanks very much. Questions?
Simone, very interesting work. I have a curiosity. This power spectrum slope that you infer for the GRBs, how does correlate with the most standard characterization of this curve, the variability, for example, you know, the variability of Ramirez-Ruiz, Fenimore, because we had a work some time ago that we showed that this variability is a parameter that correlates with the Amati, with the scatter of the Amati correlation, yeah? So I don't know if this slope that you are finding has something to do with this variability, and in this sense could be correlated with the scatter of the Amati correlation or the Ghirlanda correlation.
We try to connect the slope of the power, but the problem is that the other method used to characterize the variability, they are model dependent. I mean, in this case, using the power density spectrum, the power of the power density spectrum is you are completely model independent in the characterization of the variability. We try to correlate even the EISO in this peak EISO and maybe the slope of the power density spectrum, but we didn't find any evidence of narrowing correlation of. I know that there were other kind of correlation which involved the Amati introducing the variability, and they found something narrow. But I remember that there were some issues with that correlation.
The problem is that with this variability is model dependent, as you say, and it's very artisanal how you obtain, and so I find this power spectrum is much more powerful.
The issue was that,
yeah, but.
Questions?
Sorry, I was thinking in terms of the long gamma ray bursts and your variability analysis in the prompt. As you say, there are many different models for what might the origin be. It appears actually that a number of different situations might give rise to GRBs. No, there are several very distinct models that might all of them give you the same phenomenology. No, so it seems that that GRBs, especially the long ones, might be composed by distinct classes of objects. No, physically distinct classes of objects.
Yeah,
a couple of months ago, working with Maria Giovanna Dainotti in Stanford, we found that some of these correlations between prompt and afterglow properties can be narrowed, can give you very narrow, much narrower correlations if you restrict yourself to a very specific class of long GRBs. If you dump them all together, you get a broad sort of correlation. But when you start looking at ways to isolate a sort of particular class, like getting rid of the ones with supernova associations or the X-ray flashes, etc., try to zoom in as much as possible into one particular class of objects, you get much tighter correlations. I was wondering if it'd be interesting to try this kind of variability analysis
just for a
just for a subclass, not to try to start defining intelligently defining subclasses and see if for a subclass, when you would hope you are not lumping together very distinct objects but isolating a particular type of progenitor, things might look better.
Will be a very interesting analysis.
We could try that, yeah, sure. Okay.
I was just interested in the polarization detections. Was it linear or circular?
Circular polarization.
Circular. So did they have estimates of what the magnetic field strengths in the jet was? Can you remember?
I don't remember. I have to watch on the paper.
Any other question? No? Okay, let's thank Simone again.
Thank you. Is